Good afternoon, everyone. It's time of day to get going. Thank you for coming. We are here for Plenary, the next generation. We are really here for a discussion and for some interesting new ideas. And the conversation is going to take us from some projects here on the surface of the Earth into Earth orbit, and to projects for the surface of the Moon, projects in between here and Mars, and projects potentially eventually for the surface of Mars, and maybe even asteroids in deep space after that. And the ideas are very far-ranging, things that can be implemented today, right through to things that we're going to need to enable exploration in the decades that are coming. And these panelists, the six young Earthlings sitting here before you, they were competitively selected from all around the planet. They were selected by several of the committees that are associated with the IAC and the IAF. I could acronize them for you, but there's the Workforce Development, Young Professional Program Committee, Space Education and Outreach Committee, Entrepreneurship and Investment Committee, and the Human Space Endeavors Committee. They all work together, and over 60 applicants from all around the world applied to have a chance to be here. They had to put in a really shorty little YouTube kind of a teaser of what their idea was, I think, what, 15 seconds or something like that. And from those, they asked for further effort from 20 applicants from all around the world, just using technology. And these folks participated in that on a 3-minute video. And from those 20, the 6 people are chosen that are here with us today. And you'll see it. It's what we're really looking forward to is the questions afterwards. They're going to get up and we'll show a teaser, then they'll get up and talk about some of the details of what they're working on and ideas they've come up with, and then we'll get into Q&A afterwards. The videos, if you want to see the videos that they submitted, those 3-minute videos, you could go to the IAF website, and I've gone and had a look at them there. If you do have questions, the way we'd like to do it, just to keep it organized, is just there's paper available. There's some people in the aisles holding up pieces of paper, or write it on your own paper. Just hand it to one of the runners anytime during any of the presentations, and they'll just bring them up to me, and I'll get through as many of those questions as I can as we go here. So, did I miss anything? You guys all set? All right, any questions? So, a really interesting mix of papers that were chosen from around the world. And so that was just a brief little video version of it. Let me just introduce the people as we come down the stage here. On the far end is Andreas Honig from Germany, from TSAT Spacecom, part of Airbus Defense and Space. Next to Andreas is Victoria Alonso Perez. She's from co-founder of IEEE Tech and CloudStat, also in Uruguay. Next to her is John Walker. John is from Tohoku University in Japan, but originally from Canada, from here. Helia Sharif is who was at Carleton University here in Canada, in Ottawa, in fact, when she submitted this idea to be ready for today. And then Idris Said is just graduated in England, in the United Kingdom, from Cranfield University, but he's French and Moroccan, so he's from Earth. And then Christopher Vasco, who's also from a bunch of different places, from the Eindhoven University of Technology in the Netherlands, but originally from Austria and Hungary. So these people from several different continents and a whole bunch of different disciplines here to talk about a bunch of different things today, and a pretty neat part of IAC this year. So what I want to do is one by one have them get up and give just a 2 or 3 minute summary of the work they've been pursuing, just to maybe just twig some sort of thought of yours or question of yours. So let's just do it sort of sequentially. We'll start down on the far end with Andreas, if that's okay. So you have been focusing on something that I think has a lot of application right now, which is combining citizen science with things that are going on in orbit, a distributed sort of ground network. If you could get up and give us a summary of that, that'd be great, please.
You're absolutely right, Chris. Our team, our constellation team, tries to connect space to Earth via the distributed ground station network and the internet. And we do this because we really believe that we can support the global space community and even small CubeSat missions here on ground. And we do this with a lot of ground stations, hundreds and hundreds of ground stations in people's backyards, and setting up a global grid that allows permanent tracking and communication. Our goal is that we have is as cheap and simple as possible so that everybody can join and set up their own ground station on ground and help space missions in orbit. And we do this by applying simple technologies and existing techniques here. For example, small TV sticks that can be turned into receivers. And I actually have one with me right now, our ground station. It is so tiny, it fits inside my hand. And we use a lot of these in a way, we call it the reverse GPS, and similar to GPS, where you receive a lot of signals in your TomTom device. We will receive one satellite signal at a lot of ground stations here on Earth. The result will be the same. The more satellite signals you are, or the more ground stations you have, the better will be the positioning. The reason is we do all this is that sometimes CubeSats are not delivered into the right orbit, and for some days, operators don't receive their communication signals from the satellites because they don't know exactly where it is. And that is the part we are helping them in this way, because perhaps we are not as accurate as those existing tracking services around, but we will be faster and cheaper in providing the position of the satellite, and it is really essential for the first contact after the deploying phase. And in the end, everybody shall benefit. The operator will get his satellite position faster, and you, the general public, will have a great space experience in helping an existing space mission around. Furthermore, the operator will get a direct connection to remote places everywhere on Earth and will be able to deliver important data like emergency forecasts, weather forecasts, and so on, or just deliver pretty science pictures. And speaking of participation, we're already doing this. For example, we are open sourcing our software and hardware, and we are taking part in coding campaigns like ESA and Google Summer of Code. And concludingly, our distributed ground station network is an expansion to the existing satellite communication system around, but only consequently involving the global internet community. So let's connect space to Earth. And I would really like to start with Victoria's Drones in the Sky. Thank you.
Thank you. It's an interesting, just thinking outside the box of recognizing that there's a problem and taking advantage of the distributed network and sort of the support of people around the world, and just thinking of one enabling technology that links the two together. I had a chance to fly on the shuttle twice and the Soyuz once, and the complexity with which we tried to figure out where we were in orbit. For the Soyuz, the best one is right down in Baikonur, Kazakhstan, this enormous, super precise tracking station that looks for the Soyuz as it comes over the horizon and then tracks it the whole way across, and then as it disappears, and then does the math backwards, figures out where it was, and then extrapolates Kepler and to try and figure out where it's going to be in the future, and then uplinks us that data so we know where we are. A really obtuse and money-intensive way to figure out orbital mechanics, and I think it's a brilliant idea. So thank you for explaining it to everybody today. Next, I would like to introduce Victoria, who is here from South America, and she, if you remember from Jeremy and David's opening ceremonies, she is the bing entrepreneur.
I don't have the watch though. Yeah, too bad. So there are many things that were actually designed for a specific industry and then were used in a completely different one. The aerospace field is a very good example of that. Let's think of how many things that were spin-offs from the space industry, such as, for example, scratchless lenses or some sorts of insulation materials. And so in my case, I kind of did that. In 2001, my country suffered a lot from a disease that struck our main source of exports, that is the cattle. Uruguay had losses of like $500 million, that for a country is a lot of money. And it not just only affected the farmers, but the whole society. So I started thinking, how can there not be a technological tool to actually early detect the outbreak? Because if we detect it early, then we can probably do something to avoid this from happening. Back then, I didn't even have a cell phone, so I couldn't do much. But then, after studying engineering and working a bit in the aerospace field, I realized that there are tools. So that's when I invented ChipSafer. That is a platform that can track and early detect certain anomalies in the physiological parameters of the animals remotely and autonomously. So basically what I do is I put a device on the animal that contains a GPS. This device also senses certain physiological parameters. It sends all that information to my company server. The information in some places has to be sent by satellite in the remote areas. Then I process that information and I generate statistics to help the farmer. So basically, ChipSafer, what it does, it's a tool to early detect diseases, to combat, also to help with cattle rustling, that is a very, very big issue, and also to help the farmer improve his production. In order to commercialize ChipSafer, I decided to co-found IEEE Tech, and so I became an entrepreneur. It was a bit hard at first because I didn't even know what a venture capitalist was or many business things, but it was super exciting. So exciting that last year I also had an idea about drones, and I co-founded a second startup, which is CloudStat, that we are 3D printing drones, basically because in Uruguay it was really hard to import the components for the drones. So we decided to just 3D print them, and we are doing them all ourselves. And we're using them for different applications, such as precision agriculture or monitoring of power lines. Thank you.
Thank you, Victoria. So recognizing, especially in our home country, a really serious agricultural problem, but then applying both engineering and even space-based solutions to it. I thought it was great when she said, starting up my own company was a bit hard. Yeah, I bet, a bit hard, understatement. But what a lovely connection. And to think that they're 3D printing airplanes, 3D printing drones. To try and use technology to get around some of the historical obstacles of transportation and importing and things. So really clever ideas. Lots of questions come to mind. Next, off the planet. Our next speaker is researching and developing tethered robots for exploring lava tubes on the moon and maybe even beyond. John, so why tethered robots and why there?
Well, I'm really fortunate to be studying towards a PhD in Japan under Professor Yoshida. And actually, my research is in lunar cave exploration robots. And my research also supports the Japanese Google Lunar X Prize team, Team Hakuto. And basically, we have 2 rovers, and of course, both of them can meet the main requirements of the Google Lunar X Prize, which is to travel 500 meters. But we're really more excited about a science mission we can do in conjunction with this. So what we have is 2 rovers. One is about 7.5 kilograms, and one is about 2.5 kilograms. I think you can see them on the screen now. And the idea is the large rover can tow the small rover to the edge of a suspected skylight or cave on the surface of the moon. And so just like on Earth, we suspect that there's lava tubes on the moon, and in some places, these have collapsed, possibly leaving entrances into caves. Of course, the lunar environment is very, very harsh, but inside one of these caves, we think the temperature is something like minus 40 degrees Celsius day and night. It's also protected from radiation and lunar regolith. So these are just perfect places to try and start a lunar habitat, which saves a lot of the work. And so in order to explore one of these features, a tether is really required. So once you have a rover on the surface of the moon or some other place, it's such a precious scientific instrument that really, unless you have a way of retrieving it from a dangerous situation, you just won't send it to explore something potentially dangerous. So to send it into a cave, we need a tether so it can drop in, explore around the bottom of what we think is a cave, and be able to be pulled back up and do its next mission. And on top of this, we're actually using a lot of off-the-shelf components that have been developed for the microsat and CubeSat industries. And we're partnering with a company that provides services to land on the surface of the moon. So we're finding we're really at a point where there's off-the-shelf solutions even to get to the surface of the moon. So these kind of small robots, in addition to the very interesting scientific exploration mission that we're doing, this type of technology, it can really be used for several small companies or several universities to actually get together, get on one lander, and go somewhere interesting. So just like this kind of collaboration that happens with universities now with CubeSats, many universities get together and send 6 or 7 CubeSats on one launch vehicle. Just around the corner, we can do this with rovers as well.
Thank you very much. It's just like rappelling or belaying robots down into a hole on the moon. I also think it really shows his Canadian roots that he thinks minus 40 is a pretty nice day. Down, it's only minus 40. It's nice out. But of course, as we go back to the moon and eventually settle there, a couple of the big threats are the moon's rotation rate is so small that the intense sunlight, the guys who walked on the moon, they never get a break from the heat of the sun. So cooling a habitat or a spacesuit or whatever is a real problem. And then, of course, the fact that there's no atmosphere or magnetic field to protect you from the radiation of the universe. This solves both of those problems, and you don't have to build it. You don't have to have a solar-powered bulldozer to build your first habitat and move the regolith around. Clever, looking for in situ, not only in situ resources, but in situ habitation. So we could be the moon's first cavemen. It's a great idea, and thank you for explaining it. Okay. Communication is, of course, even over a short distance, is a big problem. Helia is talking about how to deal with the communication problems that we get when we try and travel further out into the solar system by making the robot smarter itself. How exactly are you doing this?
Thanks, Grace. Well, actually, the main focus of my master's thesis project was to overcome some of the main space robotic challenges that we face today. Because of the large distance between the planets, it takes approximately 40 minutes for a message to travel from Earth to Mars and vice versa. In addition to that, you have a very limited uplink opportunity where you get maybe about a few minutes per day for line of sight communication. And to add more to that complication, you have limited resources. So that can be anything from availability of the crew on site to power source on board the rover that add extra strain to the planetary exploration missions. So it's really ideal to have these autonomous rovers, fully autonomous, that can perform the exploration mission all on their own and perform it efficiently so you can save up some time and proceed with the mission itself. Now, there are lots of rovers out there. The latest and greatest one that most of you probably know is Curiosity on Mars right now. And it has some autonomy capabilities. It can path plan to go from point A to point B by itself. It can avoid obstacles. But once it reaches that target, that sample of rock that it wanted to look at, it still needs to take an image of the rock, send it back to Earth for scientists and researchers to further analyze it and decide whether it's interesting enough to evaluate it more, to proceed with more analysis before the rover can touch anything. So that's a lot of delay. You have to wait for a long time before you can decide whether it's interesting enough to proceed. And of course, this is where my research comes into play. I've been looking at different ways of training the rover to think like a geologist and perform this mission with little or no human intervention. Now, there are a lot of geologists out there that use different tools, a variety of tools to perform analysis on rocks. However, I wanted to design a rover that relies on what's already on board the system, because we have limited available payload on board when we were sending the rover onto another planet. And I wanted to design a robust system that's able to also perform this analysis as accurately as possible. So the way I do it is I take images of rock samples, and I apply image processing techniques to extract rock textural information, anything ranging from contrast to tonality to angular second moment, to extract these information from the rock's patterns and then further analyze it. Then, using probabilistic theorem, I'm able to evaluate what is the probability that the results that I'm looking at from this sample of rock are similar to what the rover has seen before and has cataloged it in its memory in the past. So just like the Terminator's character in the movie, as the rover is approaching its target, this next generation of rover, it's going to be able to start analyzing the type of rock that it's seeing and try to guess what type of rock it's about to analyze further when it reaches the target. So if it thinks, as it's approaching the target, that the rock it's looking at is not interesting enough for further analysis, it can quickly and autonomously reroute and path plan to the nearby target and save a lot of time in the process. So the next generation of rover is able to autonomously perform these missions and analyze rocks, allowing the crew and the mission control to focus on more critical work at hand. Thanks, Chris.
Thank you, Helia. I see the parallels with 45 years ago is really strong, where we didn't have the miniaturization and the sophistication of a rover do that, but they were sending people to the moon, and they tried to give them the same sort of skills that Helia wants to give to a robot. They took John and Gene and Buzz and Neil and took them to New Mexico and took them to Hawaii and to Iceland and even to Sudbury, and tried to teach them so that they can make autonomous decisions and recognize goodness and recognize scientific interest and make as many decisions there before they check back with the real expertise back on Earth. But it's interesting that we're at the stage of doing that with robots now. So thank you very much. So shifting a little bit, we've talked on the surface of the Earth, orbiting the Earth, on the Moon, and then maybe even on Mars. But of course, one of the biggest obstacles to traveling far from the Earth, once we get out of our bubble of atmosphere and our bubble of the magnetic field, is radiation, and then also trying to build a closed-loop environmental system. And those are two of the things we're working on, trying to understand better and fix in space exploration. And this is what Idris has been working on. Can you talk about your idea, please?
Yeah, sure, Chris. Indeed, as humans, we're very dependent on many things here on Earth. We can't live without sufficient water, food, or sleep, and these needs, amongst many others, are absolutely vital in space as well. In fact, we can't take another giant leap if these kind of very basic things are not solved in space and harnessed. Unfortunately, there are other, much more complex challenges to face, and radiation is one of them. Radiation is widely known as the major technical hurdle for long-duration manned spaceflight. And that is because we don't want to put our dear astronauts at risk of cancer, not to say death in some cases. Besides, another issue which has a tendency to get forgotten is waste management. In a long mission, large amounts of waste are produced, and it is essential not only to carefully contain them, but also process them, as they can contain some precious elements like water, which is required to sustain life in space. So far, I think you all know about this, but now I want you to ask yourself this question: what if it was possible to try to link these issues together so that one brings a solution to the other? And that's where my project comes in. My idea was to create a multifunctional system that would be able to recover water from both solid and liquid waste, dry and store and contain the remaining noxious materials, and use the whole system as an efficient shield against radiation. I was inspired by nature to design this multifunctional system, which I call the artificial intestine, and here's why. I looked at how mammal intestine worked, and I found that it used peristalsis as a way to efficiently transport the waste or the food, depending on where you are in the process. And for the design, I looked the modules that is made for this peristaltic system can be plugged together and efficiently transport these noxious materials. It is designed to autonomously transport these waste using linear peristaltic actuators and semi-permeable membranes for water filtration. As you all start to know, I'm a big fan of biomimicry. So I also looked at how nature could react to radiation. And the question to ask is, where on Earth can we find radiation? Well, if you have a nice walk someday near a damaged nuclear reactor, you'll find that there is a lot of radiation there. And it has been recently found that some algae and fungi, similar to the one included in this small box, and I said similar because the real ones are very dangerous, these extremophile were able to develop a chemical shield based on melanin, and thus thrive in these highly radiative environments. Researchers assessed these properties and synthesized the molecule for medical purposes, and I then transferred it to this space application. Of course, we can use this molecule directly as a shield, but to make things more interesting, what if we could grow these fungi directly in space, feeding them with the waste, with the nutrients contained within the waste? I'll leave the question open, but as you can see, my concept lays the ground base for future processing techniques, and these could include plasma, for instance, and I'll let Christopher discuss his idea right after me, but hopefully someday, we will be able to solve natural problems using nature itself. Thank you.
Thank you, Idris. Imagine that if one of these 6 people was on their way to Mars sometime in 30 years or so with a spaceship wrapped by an artificial intestine that is using peristalsis and osmosis to both solve the problem of waste management as well as to protect the crew from the radiation itself, and using a naturally occurring growth that can actually thrive in a radiation environment. That would be turning lemons into lemonade, sort of in a whole new way. Just a reminder, we just have our last introductory speaker here. If you have a question, please just stick your hand up or write it on a piece of paper. They'll bring you a piece of paper and pass it to the aisle, and we'll get to questions here fairly shortly. Our last introduction, Chris, you are a PhD candidate in the very final phase of, oh, by the way, my daughter turned in her PhD dissertation, 308 pages, this morning. I'm a very proud father of my daughter today. And Chris is just, you're like a month away, I think, from being finished. But not just working in plasma physics, but cold plasma. If you could explain it to us, please.
Yes, thank you, Chris. I gladly do so. And I have to say, I'm really, really jealous there about that last month. Well, if we're ever going to send humans back beyond low Earth orbit, we will be having a massive problem with resources and the big need for new technologies. I guess this audience knows about that. And I hope that the research I've been doing for the past 4 years will be one of those new technologies to be applied there. So I've been working with, bear with me, long word, non-equilibrium atmospheric pressure plasmas. So I think plasmas are very well known in this audience here, and our space cadets think about this beautiful, big interplanetary nebula, which are just astonishingly beautiful. But these plasmas are very, very different because they are tiny and they are cold. And with cold, I mean you can actually touch them, as you might have seen from my video. I mean, that's a pretty cool thing that you can actually touch your plasma. As a physicist, you don't get to do stuff like that very often. So the moment we figured out that we can touch the plasma, this is what most likely happened a few minutes after that, if you can bring up the next slide. Yeah, we played around with it. And you might be wondering, what is the interesting property of these plasmas? And that is their superactive plasma chemistry. The chemistry that these are having is just astonishing. So if I use helium and I mix a bit of water vapor into it, I light the plasma inside that discharge, I will be having 1,200 different reactions going on simultaneously. Well, most of the species which are a result of these reactions will not survive for a long time if they leave the plasma. Some of them will. And that's the interesting part about it. So in our example with helium and water, you can actually produce hydrogen peroxide out of water in a gas phase, and you can put it to an application immediately. Hydrogen peroxide can be used as a disinfectant. It can be used in systems such as the one that was presented by Idris. But it is also rocket fuel, or it is the stuff that we use to dye our hair. So it is a very versatile molecule. And all I have to do in order to make hydrogen peroxide is basically apply a bit of high voltage to a little block of glass. This is basically nothing else. The camera can show it. It's a simple block of glass with 2 parallel plates, a gas in and outlet. And what you will be doing is, if you have a field across it, you will be having a plasma in no time. And the power supply to do this, you can buy that off the internet. It's $400 and it's just really, really cheap. This technology is not new. We are not doing new things. Matter of fact, I'm sure all of you have cold atmospheric pressure plasmas at home. And right now in this room, the spotlights we are having, they might not be the cold ones, but they are plasmas. The screens we are looking at, they are made of plasmas. So we are aware of this technology, and we have been using this technology for years. Now, if you remember that image that I had up for a second, we are very, very surprised what happened when we touched the plasma suddenly, because it turns out you can disinfect wounds and you can heal wounds with a plasma. We had no idea why. So matter of fact, there are now plasma designs out there that let you wrap a plasma around your skin and you can wear it like a patch and it heals it. Because we have now trials in Germany that are using plasmas, and it turns out that bacteria really do not like the exposure to any kind of plasma. And skin cells, for some mysterious reason, do love it. So there are wounds that would not be able to heal on their own, and you apply a plasma to them and you can heal them. And this is why I think that this kind of cold plasmas and this plasma medicine is going to be one of the tools our people will need if we are returning to human space exploration. Because not only are they're really tiny and easy to do, they just need a bit of power to operate. They are fitting perfectly in those tight mission parameters of small mass and tiny, and it has to be reliable. So that's exactly what we need to take with us on the way. And it will help us to save a tremendous amount of resources, because every time my astronaut cuts his finger or has a little blesser somewhere, instead of using something that will have to be delivered from Earth, you can use something that you produce on the site, and maybe even use something you find inside to produce rocket fuel, for example. So I hope that we will still have to learn a lot about this chemistry that is happening, but I hope that the future of space exploration will be aided by little tools that are glowing, tiny, and maybe even 3D printed. Thank you.
Thank you very much, Chris. He mentioned at the end rocket fuel. People may not know the Soyuz spaceship that has been taking people to early space stations and Mir, now the International Space Station, for several decades. The Soyuz, after it undocks from the station and starts to fall into the atmosphere, the only fuel that it's using in the atmosphere is hydrogen peroxide. It's turned out to be a nice, simple, reliable, very stable, long storage fuel, and that's why they use it. And the fact that we could maybe produce that in orbit using a very simple technology that also could maybe decrease the size of and the necessity to replenish our pharmacy that we have up on the space station as great application. So thank you very much to everyone here. That's a really nice cross-section for conversation with everyone, and we received a bunch of questions already. So what I'm going to do now is, if you have questions, please continue to pass them up. I'm just going to cycle through them and ask each of the individual panelists up here to comment. I'm going to start with you, Victoria, if that's okay. You mentioned, I think if I was listening properly, you're not just the sole founder, but you are the co-founder of your startups. And I wonder, does that make it harder or easier to be a co-founder?
No, it's definitely easier to do this together with someone. This is actually, you have to cope with so many things. Business side, technical side, marketing side, it's like everything. So basically we do everything together. In IEEE Tech, I have one co-founder, and in the other one, I have 3 co-founders. And actually, they are very disgusting days, and a co-founder or business partner can really save your life. In my case, it was kind of literal. Some days ago, one of the cows, it was completely my fault, I put the chip wrong. So, of course, the cow went to the middle of nowhere, lost her chip. I saw it on the computer that it was lost. So we had to go to the middle of nowhere. I had no cell phone. I left everything in the car, and we started going around. The grass was like this high, and I was going around, and there was like a pool of excrement to which I completely fall into. I started going down and down and down, being terrified of dying in a pool of excrement. I was stuck there, so no swimming, no anything.
This is the worst quicksand in the world.
Yeah. I start screaming, and suddenly my business partner appears to save me and then take me 2 hours back to the city, smelling like, well, you know how I was smelling, to my house. So yeah, having a co-founder is really, really important.
Do you have trouble getting new investors? Thank you very much. There's a question here, and it's for Andreas. And it's I'll just read the question. It says, most CubeSats and other small satellites only have a single or maybe 1 or 2 dedicated ground stations to receive their data or for imagery or whatever. The question is about the data protocol. Is there a defined data protocol or method of aggregating the streams that are coming down over the internet from your distributed backyard ground station network that would extend the utility of small satellites and would help support efforts, say, by developing nations or other places? What is the status of the data protocol?
Currently, we checked this a lot during our design phase. So we found a lot of protocols that have been used so far, and I think it won't stop there. So this thing here is called TV dongle for software-defined radio, and this gives us the freedom to implement whatever we want, because we're just recording something and we can post-process it. And if I'm not sure who asked this, so please come back to me after the show and tell me what kind of protocol you would like, because we can implement everything and just figuring out what we have received before. So we wanted to have complete freedom, so we decided to use software-defined radio instead of implementing it in hardware or whatever. So we know that the CubeSat community is actively involving and evolving in this thing, so we don't want to use 100 different protocols. So we wanted to have it really, really, really flexible, and that is why we selected software-defined radio.
Thank you very much. Next question from the list here is for Helja. It says, so the robot geologist, of course, is going to have some level of artificial intelligence using sensors and then logic. Do you think, I'm sure you have, but do you think this type of skill would be useful for other applications, like whatever, a robot doctor, a robot medical clinician, or a robot surgeon, or have you thought about what level of the same type of idea that you're working on is applicable in other fields?
Thanks for the question. Of course, this system is something that you can train it to focus on other applications. So that could be anything from mining industries, for rescue missions. Maybe you want to send the rover to a hazardous environment that you don't want to expose additional crewmates to for rescuing somebody that's trapped somewhere. So the applications range in different departments, but specifically why we focused on exploration mission was because of where the funding came from and what the project required us to do. But the system is capable to be applicable for other uses as well.
Thank you. I just love going from planet to planet and from the human body to the surface of Mars and recognizing both the power of the invention of technology, but also the power of the human ability to cross-correlate and to look at how this might work somewhere else. Idris, there's a question here, and I'm not sure if you've looked into this specifically, or maybe it's something we as a scientific community just don't know yet, but how well do we understand the radiation profile? And in the question it says, how can we correlate the radiation profile in the upper atmosphere and beyond with the nuclear radiation profile, for example, next to Chernobyl that they're capping there right now on Earth? What do we know about it, or what don't we know yet?
Yeah, okay. So for this type of fungi that actually have been found near these nuclear damage reactors, it is important to know that it's a very recent discovery first. So researchers are still trying to understand how the process is working, because it's really rare that we can find a living organism that can develop a shield against radiation. So for the moment, these researchers are still trying to synthesize. They have synthesized the molecule, which is a great thing. It's a great advance in this kind of things. But yeah, there is still lots of things to be done before we can actually put these shields in space. And as every space technology, we have to do intensive testing, and this has to be done first on Earth. But I foresee some application in space too, and I don't know if you have heard of it, but they have found some fungi in the International Space Station. They're still trying to see why did they get there, and so the thing would be, why not purposely take this fungi and put in this International Space Station and understand their properties. So I completely agree that, yeah, there are still many things to be done, but I'm quite optimistic, and hopefully this is going to lead us towards something very great.
Thank you. So feel free, if you have another question, if there's some area that is of interest to you, please pass the question in. John, your robot, the two of them are linked together by a tether. And we've had tethered satellites that have had some mixed success, both manned and unmanned from the space shuttle. And one of the, I don't know if it was a surprise, but definitely one of the strong lessons learned from the 12 people that walked on the moon was the incredibly abrasive nature of the dust and the bits of particles without natural weathering that we have on the moon. So what is your tether made of, and why?
So our tether is made of Dyneema, which is a synthetic fiber. It's kind of one generation after Kevlar. And so our strategy for dealing with the abrasive properties of regolith is just having enough diameter to last our projected mission length, which is around 2 weeks. So that's just the engineering that we do there. And actually, we're using a completely passive tether because with two robots, one of the obvious advantages is that they can be redundant. But in order to be redundant, they both need their own power supplies, radio communications back to the landers, and so on. So having an active tether with power and communication between the two rovers isn't really an additional thing we require.
And so you've settled on, rather than a wire rope or a chain that you might have on a traditional winch somewhere on Earth, you've settled on the next generation of Kevlar. And what were your design drivers in settling on that?
Basically, just minimizing mass and minimizing size. So really typical requirements for a space mission.
Okay. Thank you. Okay, question down, Chris, down on this end. Right towards the end, you were talking about the cold plasma health benefits, and I don't know what level of testing that's at. And the question is, you talk about skin cells healing with plasma. What level, what type of injury that we might face on the space station, how robust is the healing from that?
Okay, so what we have seen so far is the first level of testing that we've been busy with is just what kind of bacteria can you kill. And actually by accident we figured out that the skin cells are growing, and now what we are looking into is infected wounds. So I'm thinking now the first level of in vivo tests actually with patients are burn wounds or these diabetic ulcers that develop and that are infectious. And they need a lot of treatment. They heal over long extended periods of time, and we have seen that applying treatment with a very similar jet than what I've presented here speeds up the healing. So we are talking about increased healing rates of 25% sometimes. So this is what we think about big cuts and infected wounds.
Okay, thank you. Next question came in from Twitter. The question is, thinking, you guys are the next generation, but you're not kids. So of course, thinking about the people after you. And I'm sure you all ponder it or are going to think about it soon. The question is, what can you do or what needs to be done to help the next generation after you? What have you learned and what do you think is a pressing issue for the next generation? Victoria, do you mind answering that?
Yes, I think that one issue is well, some things in the educative system needs to be changed. Like, for example, now it's known that there are different types of intelligence. So actually going to enhancing all the different types of intelligence and not making everyone just go through the same curriculum, I think that is really important. And of course also enhancing the creativity. I think that maybe now the educational system in some cases might be turning down the creativity.
Yeah, I would like to tie in there. I completely agree to this view because what we are seeing, I think those who are doing like this end now, not the entrepreneur pin, but the academic pin, it takes us a tremendous time to get where we are to do our PhD, and it's a lot of hard work. I'm pretty sure all of you know that. And we are not really being exposed to other fields who have gone through the same process in the couple of years. So I'm working with biologists and with chemical reactor engineers, and you would assume that this is very, very natural that we talk about the same things. But even when it comes to conducting experiments, we have completely different ways of doing things, and we are not being exposed to that. So the educational system, while we are trying to breed the best out of us and really teach our next generation how to be the best in their fields, we are not really exposing them to other fields. And then the conferences like this, for the first time you realize that, hey, they're using the same unit and they're using it for something completely different that I can't relate to. So that is extremely important, and we're not doing that too much.
I completely agree with what you said, Christopher. One thing that is related to my project was that I was able to interact with some researchers that were working in the medical field. So I'm from a mechanical engineer background, so it's completely different. But what I really loved is I found their paper, so I sent them an email, and they were very, very happy to help me. And I got to understand some things that I would have never learned about. And I think that's something, like in our generation, if we want to continue in that direction, we should foster these interactions between different areas, from different type of engineers, researchers, medical people. So, yeah.
And where we are now with the almost effortless level of connectivity that we have around the world. When I went through university, what was in the textbook and what the professor was saying was, and whatever I could find in the library, that was the source of all knowledge. And you had to draw your particular level of understanding from that. And now, of course, it's such a wider field that we need to, I think, somehow make that part of how we teach young people so that they get that right from the get-go. Here's a question for Helja. And this may be a philosophical question for everybody in the room. It's one that I've heard discussed many times. The question is, do you think that advances in your work may replace manned spaceflight?
Never.
Oh, good answer. Thank you.
I hope not. I'd like to go at some point myself to space, so that wouldn't really be helpful. I think right now we're not ready to send humans to Mars or other planets that are far away. And this system is just a design that's supposed to help the crewmates perform these dangerous missions that you don't want to put the life of an astronaut or a crewmate in that situation to perform the task. So really, this is a system that's supposed to help them, not replace them, and hopefully just for the time being, allow them to explore other planets and explore these hazardous environments until we're ready to send the human to do the proper, thorough study of the planet. This is just to make it a little bit more efficient, the performance of the exploration missions. But I don't think we're anywhere close to the level that a human can analyze something. We can't train the rovers as well as a human would be able to.
Does anybody on the panel have a dissenting opinion? Like, think it's better to send rovers forever?
I think there's always room for manned spaceflight, but it's really important to use rovers to really leverage the amount of places and the reach that we have. So you can send many rovers to many different asteroids, planets. Of course, orbiters and other types of spacecraft are also important. You can't send humans everywhere. You can't take the time to develop a safe way to send humans everywhere. But you can use robots to explore many places, pick one interesting one, and then go on with the manned spaceflight.
I sort of see it like, very simplistically, like a lot of people every year go to the Taj Mahal. And you will never take as good a picture of the Taj Mahal as already been taken. You will learn nothing factual about the Taj Mahal that you can't already know just by reading about it. But yet, I don't know what the number is, hundreds of thousands of people every year go to the Taj Mahal because it's not just the data and it's not just the temperature or the color or the crystallography of it. It's the human experience that really matters to all of us. That's the fundamental reason to explore anything. That's right at the core of all of us. So I agree that there is a place for both, and there always is going to be a place for both, whether you're going around the surface of the world or into the third dimension. And we just need to recognize when it's time for which, I think. Makes sense. Andreas, here's a very technical question for you. What are the power of internet or communication requirements of your system? So could you minimize it, taking into account countries where there's very limited either electricity or just straight communications capability? What is the minimum?
And right now, this kind of sticks can run on your PC, on your laptop at home. But if you cannot afford this 60 whatever watts to run your PC, they are really, really simple. The software is open source, and the open source software had been ported to other Linux-based systems like BeagleBone, Arduino, I'm not sure, but BeagleBone and other smaller systems that only consume some 10 watts of power. So I think you could also plug it to a solar panel and then throw it away. And then when a satellite hits it, and also the sun is there, of course, you can use it from this position to track. So these are really simple. I don't have a number right now, but if you want to have more numbers, I do a paper presentation 1 hour in the B4 session. So come on, I will explain more, but these are really simple. It's not a big deal.
It's great. Almost I know there are some surfboards that have been released that are self-propelled just through the mechanical wave action, that are solar powered and that are transmitting a bunch of data, and they just keep releasing them into the Pacific, and unmonitored, fairly inexpensive, and with the simple release of technology, it allows a better understanding of so many different things, climate and wave patterns and everything. So making it inexpensive and ubiquitous is a really cool idea. We only have time for 1 or 2 more questions. John, this one's for you. Have you thought about the characteristics that you're looking for to determine if a tube is ideal? How driving around would you choose which tube to lower your robot down into?
Basically, as I mentioned, we need to use a partner to get to the moon. So that's a matter of discussion with them, something that's mutually interesting, something that's interesting to the scientific community. But actually, in the last 4 or 5 years, there's just been so many papers published about these potential lava tubes, especially in Japan, that I think it's quite easy to find 10 or 12 that we would want to go to. And any one of those, I think, is interesting.
And how would you choose the best out of those 10 or 12? Is your part of that, or are other people choosing?
I hope that there can be some kind of scientific consensus. There's enough experts in the general scientific community that I think it shouldn't be only up to us to decide.
Okay, thank you. Here's a general question for the whole panel that I think will bring us to the 1 hour time here for all. And this is, one of the issues we face as a global community is being able to better communicate the importance of what we're doing, of exploration and space exploration to the community at large. And how do you think you address this problem, or do you think this problem is necessary to address? Do you see a role for disciplines outside of those normally associated with STEM in the solution? And go ahead, anybody who'd like to answer, go ahead, Andres.
I will start here. We are deploying a lot of ground stations and we're forming a global grid. And it was also directly in the designing phase that we want to communicate what the CubeSats are doing up there when you have direct connection to people worldwide. You can send down pretty pictures from space or temperatures from your spacecraft, and even more important, actual data, perhaps for weather forecast and flood control. And these people receiving it on ground will say, hey, this came from space, so something important is going up there, even though perhaps I don't know where it comes from. So it was even in the design decision, we wanted to have it as open as possible, and showing the people where this important data, weather forecast and more, is coming from. This is
so
our
if
idea.
you enable people access, their natural curiosity will follow, and then their behavior change will be such that that they're involved in exploration directly, just because you've allowed them to be part of it for very little initial investment. Cool. Anybody else want to talk about that? Idris.
Yeah, one thing is we never know where the innovation can come from. As I mentioned before, yeah, we need to interact between different fields. But another thing that I think is interesting is to interact between different nationalities. And I think this IAC is a great example of it, where that's what we are doing actually, presenting to large amounts of people that are coming from different fields and different countries. And I do believe that we have to continue in that direction. And probably some of you will have another idea from our ideas, and that will be great because, yeah, it's, we're going in the right direction towards space exploration and other awesome things, so yeah.
Anyone else? Victoria?
I think that, yeah, really showing that what we're doing for space exploration can actually then be used in our daily lives. I talked to people in different countries where they didn't know that GPS actually was coming from satellites, that it was something they had in their car, but they didn't really know how it worked. So I think that there is an issue in really transmitting that what we use for space can actually be used on Earth. For Chip Safer, for example, since I'm kind of using that, you can also be impacting positively the lives of a lot of people. I found out, I didn't know, doing this, that there are more than 1 billion poor farmers that depend on livestock. And really, something that for me was so usual in the aerospace field, like the GPS, and then translating it to this. And through this, the farmers cannot know that they are using something that it's actually coming from space.
So the almost a common theme is to recognize the advent of technology and then see how for minimal investment it can be applied to improve quality of life, but then also show that it can be multidimensional technology, space-based technology that is allowing a poor farmer somewhere both to monitor where their herd is, make sure it's not being rustled, but also to be able to monitor its health. Really, really interesting cross-section. Anybody else? Yes, go ahead, sir.
So I would like to tie in on that part that we can no longer afford not to be good communicators. So when I started coming to these congresses for the first time, I always heard that phrase like, yeah, educate the educators. Yeah, no. This panel, I think, is a fantastic example. If we don't learn how to talk amongst each other, you won't be able to pick up how easily you can actually explain something super complicated to somebody completely different. And then you go home and you can actually do it yourself. You don't have to be an educator. You can go out there. For example, my little blog that I brought around. I mean, if I had talked to somebody like Victoria or John about how to integrate systems, I would have 3D printed that years ago. That's my fault. I didn't communicate with these people, and I think the fact that all of us are here right now, we are training that communication. Unfortunately, we can't all play the guitar in space like you did, but that is a fantastic example, I think, that if we learn to talk to each other, we can carry our passion out of this room. And I now have, I think, a couple of new ideas how close space actually is to real life because just sitting on this panel with you guys.
We're running out of time. I just wanted to finish with this. 55 years ago, a Canadian boy was born who, as he grew up in the 60s, dreamed of flying in space, but saw no way to do it, was really combative against his parents, had a lot of really strong ideas, but no way to implement them. Basically ran away from home at 15 or 16, went, bummed around Europe on the streets, learned some interesting skills on the streets of Europe, and had some ideas, and came back and started street performing in Canada. And through his own initiative, created a performance capability that was unknown in the whole world. And some of those performers helped open IAC this week. And what's to me is interesting out of that is Guy Laliberté pursued a life very much in the arts and the humanities and trying to help us see things in a new way. But he always wanted to be an astronaut. He had just never saw the opportunity for himself. And yet that eventually led to the chance, because of the wealth that he created through his own mind, to have a chance to fly on board the Soyuz and spend a week on board the International Space Station. And I think it's an interesting alternate pattern, and it's a fairly new one. It's not the more traditional path that I followed. But there are multiple ways to not only start to explore the universe, but to achieve the things you're dreaming about. We've seen a lot of those multiple ways and different ideas being applied here on stage. And just before we all collectively thank the six of you and congratulate you for being part of this, Guy took the best of the pictures that he took in orbit, and he created this extremely expensive book that, he calls Gaia, but he provided one for each of you. Both as thank you and congratulations for being here. So on behalf of everybody, please thank our speakers here today.